Hi everyone. In this video I'm going to talk about how we can proceed with statistical inference when we have two small samples. So now suppose the two samples we have are small and they're drawn from independent and symmetric distributions. By small I mean we have fewer than 30 observations, so we're going to need to use the t-distribution. So in order for our approach to be valid, we have the following requirements. We're going to need random samples from two populations with approximately similar distributions in the sense that we're going to need to have equal population variances. Now that doesn't mean that we have to have equal sample variances, only equal population variances. And when these conditions obtain, we're able to use the following confidence interval. And notice how this is similar but different from what we've seen previously. We're using the t-distribution here for our critical value, and we have a new standard error. So this is called a pooled estimator for the population variance, and you really don't need to worry about all the details for this. It sort of goes beyond the sorts of things we care about here. It's important to know that our standard error is different and then how it's being used. Ultimately, when you're doing this, you'd use statistical software to compute this anyway. Okay, but I'll talk a little bit about what's actually going on. So we have only one population variance by assumption that the two samples are coming from populations of the same variance. And the pooled estimator is just going to be 1 minus the sample size from sample 1 times its sample variance plus 1 minus the sample size from sample 2 times its sample variance divided by degrees of freedom. So degrees of freedom here is the sum of each sample minus 2. So that's like n1 minus 1 plus n2 minus 1, or n1 plus n2 minus 2. And we're going to use this same pooled estimator approach for our standard error, whether we're doing confidence intervals or ordinary test statistics. Okay, so the pooled estimator, essentially what it's doing is bringing together information on the population variance from our two samples. So in order to account for the fact that we're using two samples for this information, we're going to write down our degrees of freedom as the sum of the sample sizes minus 2. So we want to get a weighted average of the two sample variances such that the weights are proportional to sample size. And details for why sort of go beyond what we mind, but here's the degrees of freedom. Alright, and anyway, here's an example of our one-tailed test. Looks a lot like our large sample test, but the difference is in the standard error. So now we're using our pooled estimator, of course, and we're working from the t-distribution. So since we have small samples, and since we're interested in the sampling distribution of the difference of sample means, the appropriate degrees of freedom for the particular t-distribution we're after is this one here. Alright, well here's the two-tailed test. It's very similar. The test statistic, in fact, is going to be identical. But of course we're going to have a rejection region that accommodates both directions of extremes since we have two tails, much like a confidence interval. Alright, so here's an example. Suppose we have two samples, one of 11 observations with a mean of 3.27 and standard deviation of 1.3, and the other has 15 observations with a mean of 2.53 and standard deviation of 1.16. Well, both sample sizes are less than 30, so we're in the small sample world. And we want to get a confidence interval, a 95% confidence interval, assuming we have normal populations, though we've got small samples. So given the small sample and the unknown population variance, we're still going to use the t-distribution. Well, we have 11 plus 15 minus 2 is 24 degrees of freedom, which picks out this particular t-distribution associated with 24 degrees of freedom, meaning that our test statistic at this level is going to be 2.064. Our pooled estimator is going to give us 1.489. So putting this together, we can build our confidence interval. The 95% confidence interval for the difference of means is going to be minus 0.26 up to positive 1.74. And notice the interval contains 0, so that's the outcome where there would be no difference in population means. So this would be consistent with the hypothesis, the null hypothesis, that there's no difference in means. Well, let's actually go ahead and test. So here's the information once again to remind ourselves. And I'm going to write down the actual hypothesis test that there's no difference in means against the alternative that there is. And of course, our critical value is going to be the exact same 2.064 we found before. We got to find our test statistic. Well, it's going to work just like when we built the confidence interval, but there's going to be an additional step. So we already know the pooled estimator for the sample variance that yields 1.489. So the test statistic is then the difference of sample means minus the difference of population means divided by the pooled estimator, the standard error. So our test statistic is 1.53. So that can't possibly lie in the rejection region since it's smaller than our critical value of 2.064. So we confirm our suspicion from the confidence interval and we find no evidence of a difference in means. So we fail to reject our null hypothesis. All right. So what about when the population variance cannot be assumed to be equal? Then we would need to use the Satterthwaite small sample procedure. So we have one for equal, another for unequal sample sizes. Well, suppose we have equal sample sizes, then our confidence interval looks like this. And assuming we're interested in testing for a difference of 0, our test statistic is like this right here. Otherwise, I'd have to subtract a difference of means in the numerator. What's the difference? Well, look at the standard error. We use a t-distribution with n, or 2 times n minus 1 degrees of freedom. It's exactly the same before, since sample sizes are assumed to be equal in this case. Well, what if sample sizes are unequal? Then we'll use this confidence interval and test statistics. So it kind of looks a little familiar. Here's the big difference. You're not going to be responsible for this part. The confidence interval and the test statistic are pretty tame. It's the degrees of freedom that are different. Right? And so in this situation, our degrees of freedom, we find v degrees of freedom for the small sample procedure where population variances are not assumed to be equal. This is kind of messy. It's not terrible, but it's a little messy. It's the squared sum of sample variances weighted by their sample sizes divided by the sum of sample size weighted variances weighted by 1 less than the sample size. You're not responsible for this. In an exam type situation, I would just give you the v degrees of freedom. I wouldn't have to bother with this at all. Okay, so let's talk about margin of error and sample size a little bit right now. We can find the required sample size to estimate the difference of means reliably. This is just the same formula as for the single sample case, but we use the sum of population variances. So ultimately, this will very likely require that we use estimates for the population variances. Well, here's an example. So suppose we have prior knowledge of 2 population variances, and we want to estimate the difference of means with 95% confidence in a margin of 5.8. So the required sample size in order to make this work is 54. We get this from the formula. We just have the critical value of 1.96 squared times the sum of variances, 12 and 18 squared, divided by the margin squared. Okay. So here's a comment on inference with a t-distribution. We often don't know the population variances and therefore cannot use the exact z procedure. Instead, we'll use the t-distribution in those instances, and this is pretty common. We'll use the t-distribution quite a bit. Now, if you want to use the t-distribution, it works just like a z-score. The difference of sample means minus the difference of population means divided by the standard error. Now, interestingly, though I haven't made a big deal of this so far, this test statistic is actually not going to have a t-distribution, and that's because we have a difference of means for our sampling distribution rather than a single sample mean. Well, all this requires is a different approximation for the degrees of freedom, whichever is smaller, n1 minus 1 or n2 minus 1. So just as with inferences with standard normal distribution, we'll reject the null when the test statistic lies beyond the critical value, or when the product of the critical value and standard errors is written in this way. If we actually do have large samples, we can just apply the central limit theorem, of course, and it won't really matter if the variances are the same or not, but we can always use a variance estimator. And in this case, we would use the 1.96 as our critical value since we're invoking the central limit theorem. And lastly, a comment. So suppose all our assumptions have not been met. And so remember, each of these different sorts of tests had a set of assumptions that needed to be holding true for it to be valid to apply those approaches. Suppose not, well, then there's going to be non-parametric tests that we could use instead. So you can check the text for additional details. We're not going to cover this in the course, but I wanted to at least mention that there is a procedure and there's something we can do when our assumptions do fail. And what we essentially do in that sense, or in that situation, is we're going to want to use a test that's not going to depend on particular assumptions pertaining to an individual distribution. And that's going to be the idea.